Now, because we've got such symmetry in all of the trig graphs, there's lots of really cool facts that you can discover just by investigating any one part of any of the curves. For example, if I take a point like, say, x equals pi on 2 here on the graph of y equals sine of x, I can see that this point here and this point here are exactly the same. And this one here and this one here are the same. As I go down and get further and further from pi on 2 in either direction, I get y values that are exactly the same. You can easily write a little algebraic statement to show this. And it makes you feel quite clever once you realise how many of these statements you can make really simply just by understanding the graph. So let's say I've got these 2 points here and I've just moved a certain distance, let's say x along, plus or minus x. I can say that the sine of pi on 2 plus some angle would be exactly the same as the sine of pi on 2 minus that angle. And I can tell because if I move along here the same distance, I'm going to get the exact same result on the y-axis. So this allows us to make a lot of statements like this that can help us compare angles. Let's just throw a number in there just for argument's sake. Let's make it, let's move back to degrees so that we're just super comfortable. This is like saying the sine of 90 plus something is equal to the sine of 90 minus something. Now let's let that something be, I don't know, 40 degrees, say. Well then the sine of 90 plus 40, which is 130, is equal to the sine of 90 minus 40, which is 50. Now this is a fact that we've already seen to be true, but now we're starting to relate it to the graph and understand why it's true. Another thing I'd like you to think about is that when you look at the sine graph and you see it move through the first quadrant, 0 to 90 degrees, second quadrant, third quadrant, fourth quadrant, you can see why it's positive, positive, negative, negative. So when you're looking at your all stations to central, positive, positive, negative, negative. And then it just continues on and on. Just as we can do laps of 360 degrees, we can do sections of graph of 360 degrees. And we just keep following this positive, positive, negative, negative pattern. Once we draw y equals cos x on in a different colour here in red, on the same axis as y equals sine x, we know that they've got exactly the same shape. And if we were, in fact, to move one along with a bit of a translation, it would become the other graph. Let's have a look at how this would work. Well, if we were to take the sine graph and actually move it backwards, or take the cos graph and move it forwards 90 degrees, or pi on 2, then what we'd get would be the other graph. So we've written this here. Cos of x is equal to the sine of x plus pi on 2, or 90 degrees. And that's because we can take the sine of any angle, move it along 90, and that will be the cosine of that same angle. So we already know this works when we sub in numbers and use it with degrees. It'll work the same way in radians. And this is very much related to complementary angles. We know that in any right angle triangle, if we label these other two angles alpha and beta, if this is a right angle, these two must add to 90. And we know that the sine of one will be equal to the cosine of the other. So we can see how that relates on the graph. You'll also notice that if we're wanting to relate this red graph to all stations to central, we've seen that this is really just a shortcut to show us the sine of the cosine ratio. We have, for cosine, positive, negative, negative, positive, positive, negative, negative, positive, positive, negative, negative, positive. And we can see that the same way here, positive in the first quadrant, then negative for 2 quadrants, then positive for 2 quadrants, and on and on. And this sort of explains why our y equals tan x actually has a period that is not 360, it's only 180, because when we do have a look at where tan is positive and negative, we have positive, negative, positive, negative. And that's explained by the nature of its graph that goes negative, positive, negative, positive, starting, of course, in the first quadrant with a positive.